Everyone. So I'm at Hungerford. I work for Pebble. I'm a firmware engineer there. We're just going to do a quick little talk about some interesting things about Pebble. I'm presenting this mainly from the perspective of Pebble as kind of a cool embedded gadget. So we're going to talk a little bit less about webby things, a little bit more about graphics and some cool tricks we could do with the Pebble. So here we just see some things that Pebble is typically used for: watch faces, notifications, and a couple of really popular apps like Pandora, Runkeeper, ESPN. So the main thing about the Pebble that really differentiates us is our display. We use an EPaper display. It's very similar to e-ink. The big difference between e-ink and EPaper is that EPaper has a very high refresh rate. We can refresh about 25 to 30 frames a second without clearing the entire screen each time, like you have to do with a Kindle. We have a 144 by 168 resolution, which means we have 175 dots per inch, which is actually pretty high compared to like a monitor or TV. We use EPaper because it's very low power. We get 7 days of battery life with our screen. It's always on, it's always displaying. We do have a backlight so that you can basically see the image at night, but the screen itself is always running. So this is just a couple examples of some of my favorite apps and screenshots, just showing off the quality of the image on the Pebble. So these are the 144, 168 resolution images. And in here we have like the Pandora music player, Glance notifications app, Pixel Miner, one of my favorites, XKCD. Couple of the images in here, if you look, the bunny and then the robot in the bottom right corner, they both look kind of gray, and we'll go into that in just a second. Our screen is black and white, but if you notice, there's a couple images in here that kind of betray that look. And let's move forward. So first off, we're going to talk about Pebble from the perspective of images. A while ago, I wanted to write XKCD comic app for the Pebble. And this is pretty cool in that Randy Monroe, the guy who makes XKCD, the webcomics, he licenses all of his comics as Creative Commons. So anyone can take the images and print them on a coffee cup or a T-shirt, or you can make your own like best of XKCD apps or books or whatever. So I really wanted to make an XKCD comic viewer for the Pebble. One of the limitations is that the Pebble SDK only supports Pebble bitmap image, PBIs. Just like the name says, they're bitmaps. They're just ones and zeros for the pixels. There's no compression. They're just full-size images. Unfortunately, what that means for us is that to have the images word aligned so that we can use them with our compositor, it's going to take 3.3 kilobytes per image. The Pebble resource storage size is only 96 kilobytes for an application. So that's how much space the app has for its icons, for its fonts, and then for any like raw data you actually want to can with your app. Like if you have like a level map, or if you have like raw strings for different language support. So up here we have the first one, the Pebble bitmap image, the uncompressed bitmaps. And we see that the image is 3.3 kilobytes, which means that we maxed out about 29 images for the app, which makes it kind of a lousy comic viewer at that point. That's 10 comics with 3 frames per comic. A while back, I ported microPNG. It's an embedded PNG library to the Pebble. And right now it's on a GitHub project I have. A couple of people are using it. The great thing about PNG is that it's very lightweight, very easy to use. But on top of that, it's compressed. So I can take the exact same set of images and compress that 3.3 kilobytes down to just under a kilobyte, so 0.9 kilobytes. All of a sudden, we're talking about 106 images on average. So the first thing I want to dive deeper into was those grays that we saw in the first couple pictures. We're achieving that by doing some dithering in the apps. So you can see here, dither is an intentionally applied form of noise that we use to basically mask the fact that we just have fewer colors. So our display is black and white, but we can actually have more complex images with shades of gray, like you see with the cat there on the right. And these are the different forms of dithering from left to right. The nice thing is that ordered dithering, the third one over, is a very consistent dithering pattern where the pixels are always in the same position, so it's very good for games. It's very good for applications that just need to do like live graphics, like a TI-83 calculator game or old Game Boy monochrome game. Floyd Steinberg is a little bit better for image displays, where it's going to allow that noise that makes the grays work kind of diffuse among the entire pattern. That basically means that like your colors from one section are actually going to bleed a little bit over into the other sections, but overall the image quality is much better. So these are just a couple examples of images I've dithered for watch faces I've made. These are all open game art watch faces, all Creative Commons again. One of my favorite, this is the avatar I'm always using, the golem or the robot, where you can see there we take the original image where he's gray with glowing blue hands, and due to dithering we can basically make him look gray with glowing white hands, just have a little bit more contrast and display. The demon wolf on the bottom right isn't dithered, it's just a very high contrast image. I just really like how that one turned out. And then, as you can see there, the bunny was basically from a tutorial I ran where we are taking him from color to grayscale to dithered. So you can see the trend, like the change of the image there. So if we combine those two things, both the PNG, the ordered dithering, and a little bit of animation on top of it, we can create animated watch faces pretty easily. So this is originally from a GIF I found online called Hero Morph, and I ran it through ImageMagick, ran some dithering patterns against it, and I was able to create this pretty cool little animated watch face. The nice thing is that APNG has the benefit over just plain PNG. It only stores the difference from one frame to the next. So rather than having a max of 106 images, I'm able to get more around 200 to 250 depending on the images. So you're able to have, at 10 frames a second, a 20-second long animation. And in this example, I'm just doing the 10 frames per second. I've actually been able to show that with animated PNGs, we're able to push 25 frames a second to have a much higher refresh rate of the image. But it basically costs you how long the animation can then be. So this is just a quick zoom in of that dithered image from earlier. So here we can see with the Batman where his shirt underneath the cowl is all gray. And then when we zoom in on the right, we can see that ordered dither pattern. I always consider this one myself to be the perfect gray, where it's the perfect checkboard pattern. There's no noise, there's no diffusion, there's no like random pattern to it. It's very compact. And so our eye kind of plays tricks on us to basically make that one look like a true gray in the Pebble. All the other ordered patterns or Floyd Steinberg, your eye is smart enough that you can recognize that there is a little bit of noise there. There is a little bit of some kind of artifacting going on. But the great thing with this pattern at 175 dpi, your eye just blends it all in for you. So now we're going to flip from, those are all generated offline. So I'm making those in Photoshop or the GIMP or ImageMagick. Usually ImageMagick because it's easy just to batch things. We're going to just talk really quickly about runtime dithering. This is where we have an algorithm in the code, and the code itself is going to do the drawing. So first we're going to just look at the ordered dithering or with a bare matrix. This is basically a giant matrix that, as we're trying to draw our pixels, we pick a position in the matrix, and that's going to be the color of the pixel, the position we're currently at. This is really great in that it's extremely compact. We just have to store the matrix in code, and then we just have this color for gray. And that little dither, that little line there basically does all the drawing for us. So it's a very small code add to have your application have built-in dithering support. Am I going too fast? Can everyone hear me okay? Okay. So here's a really cool example of the Amiga bowling ball ported to the Pebble using that ordered dithering we just saw. And this is great where it's all been pre-computed. The developer, Heiko, he actually wrote all of this in Python originally to basically figure out how to make it look, how to make it run fairly smoothly. And then he ported his Python code over to C and then ran it on the Pebble. And then he's doing a little bit of shadowing effect underneath just to give it that look of that there's actually like a cast shadow. So up to this point, we've been talking mainly about how to display images, how we're going to get images working or dithering in runtime. One of the things that we recently released with our last 2 firmware updates is you no longer have to use our drawing APIs. We have a draw line, draw pixel draw polygon, and we have a couple other like draw font commands. But the thing is, if you really want to push like raw pixel speed, you need to actually render directly to the frame buffer. You want to avoid our very, I call them convenient functions, and just have the raw frame buffer access. So in this next example, it's going to be an app that is rendering directly to the frame buffer. So we see right now we're using the draw pixel command, drawing all those pixels. We're going to switch modes over to frame buffer, and we can see how much faster it is. It ends up in this application, because it's a fairly simple application, it makes the application 100-fold faster. If the screen could support it, we'd be rendering 1,000 FPS, versus the original one was, I think, 15 FPS with the draw pixel. Here, I'm just going to launch that one again. And you can see that this, again, is the bare matrix dithering, or the ordered dithering. And by the way, the thing in the background, that's our engineering boards. We use them when we're developing applications or trying to debug what's going on with the Pebble itself, where we can attach debug lines, we can figure out how the system's running. But it also makes it great when we're capturing a picture. It's not a Pebble on your wrist, so you don't have like the hand in the background. So this last part is basically going to be a combination of everything we've looked at to this point. Image rendering, direct frame buffer access for speed, and dithering to get a little bit more quality out of the screen that we have. So here, I ported a OpenGL software renderer to the Pebble, and you can see that we've got the appearance of depth. This is an OpenGL 1.2, so it's a more primitive. It's not OpenGL ES. It's not like a modernized one that has pixel shaders or any of that kind of stuff. It does have built-in lighting support, lighting sources, so it's basically casting from one light source to the pixels on the screen, and that's why as the images are rotating, they're changing colors as the sides hit the light. And this Pebble GL engine has both wireframe mode as well as like a polygon fill mode. And for this application, just to make a quick demo, I was using STL models. Those are the models that you typically have when you're printing to a MakerBot printer or any other kind of like 3D CAD tools. So I basically went on the MakerBot site, found a bunch of really interesting models, like this unicorn, and converted them to STL and then rendered them on the Pebble. But once again, this is all possible because we have this bare dithering that allows us to actually have some depth. Otherwise, we just have a black background and just a white silhouette. But with dithering, we actually get the appearance that there's some depth, some other colors going on. And also, without the frame buffer access, we'd be getting 1 or 2 frames a second versus the 20 or 30 that we're getting. And then this is another example of the Pebble GL engine. This is kind of a twist on the last one. I was originally trying to make a racing game out of this. But this is doing both the wireframe for the tunnel, ordered dithering for the checkerboard pattern on the bottom. Let me just, I'm casting a shadow for the ship, and this is actually a perspective engine, so as things get further away from you, they get smaller. So it makes it really easy to basically do a 3D environment. Like you could do like a Google Earth, or you could do a car that spins in 3D with this technique. The great thing is because in this example, we're not using a lighting source. There's no light casting to every pixel on the screen. It runs much quicker than the Pebble GL engine we saw earlier. And that's my presentation. Does anyone have any questions about Pebble? Oh, hi.
Is there a lifetime to the number of refreshes you can do on that technology?
No.
No.
Nope. It's memory resistive barrier LCD.
Okay.
So it's just a liquid crystal display. Same thing with EPaper, for e-ink, sorry.
So it does consume some energy at quiescent.
Right, so that's one of the trade-offs we have with EPaper versus e-ink, is that there's a very small amount of trickle capacity to keep the screen in the current state. But if we turn off all of the tech in our Pebble, we'd get months out of the screen alone. I think the Kindle Paperwhite is the same technology now. That's also why they don't have to blank the screen each time. Basically, people don't want their ebook readers to last years. They want them to last months and look a little bit better.
One more question.
Sure.
The floating point that's done on OpenGL, is that actually software or is it hardware?
So I was debating about presenting that here, but I wasn't sure if people would be interested. So the Pebble has a Cortex M3 processor. It's a microcontroller. And unfortunately, it doesn't support floating point. And so whenever you do floating point code, it ends up being very, very bloated. It takes up half of your code size for Pebble apps. It ends up being insanely slow. I ported over an old software fixed point implementation called SLL, Sine Long Lung Math, and wrote some hacks to allow GCC to treat it like it was floating point. So in my code, I just write everything as floating point, and under the hood, it's all done with fixed point. And it's been really nice in that we've had a lot of developers complaining that the floating point emulation, like you know, people don't realize that's what's happening in the hood, that their apps are running so slow. So we've made this this fixed point wrapper available to people, and it's great where suddenly you free up half your code size and your app runs 10 times faster. But without it, the Pebble GL engine both wouldn't fit on a normal Pebble. I could only run it on my big board, and it also just ran really slow, so it was really boring. And actually, if you, I can take a quick second, just pop it up. Actually, I have a video of the floating point versus the so let me just grab this on the other display. So I actually have a Mandelbrot app I ported over that shows the two side by side. Here we go. Oh, looks like the video's not playing on here. But yeah, basically, originally I had done a Mandelbrot viewer for the Pebble. At Pebble, every 2 weeks we get a Dev Awesome Day to work on our own personal projects. So most of the apps I was presenting here were things that I worked on in that 10% time. And one of the days I was kind of burned out, so I figured I'd do like the Hello World of Graphics, the Mandelbrot app. And unfortunately, the algorithm I was using was from Wikipedia. It was a floating point implementation. So I was getting one frame every 20 seconds. And extremely boring. And so I ported over to this fixed point wrapper. And it was actually the first time I had dusted off the fixed point wrapper in a while. And also my Mandelbrot app was going 1 frame per second because there's no sines or cosines, it's all just math intensive. And it was more interesting. Like I would have loved it if it was much faster than that, but you know, like 20-fold improvement was great. And oh, sorry. Oh, okay. But it was really nice in that there's all these old embedded tricks that kind of come back on the Pebble where it's neat where you're able to basically leverage the fact that we've got this microcontroller, we've got this EPaper display to really make neat applications without, I always say it's like you can be more impressive with less on the Pebble, where if I do like a 3D spinning world or if I do a amazing route tracing app on the Pebble, people are amazed, people love it. If you do the same thing on like Android or iOS, it's kind of a built-in app. It's things that like, yeah, everyone's got them, it just comes with the system. So it's definitely much easier to impress on the Pebble. And at the same time, I think Pebble is a better watch. Like we basically made the core fundamentals of Pebble is that it's a watch first. And that means for us the ability to tell time, the ability to get notifications, the ability to stay connected to time and events around us. And then all the other things like playing games or watching videos or any of that kind of stuff are like secondary. So yeah, that's basically.
Most of your demos didn't use Floyd-Steinberg dithering. Is it just too computationally expensive?
No, actually, it was a personal choice of mine where the Pebble GL engine originally was Floyd-Steinberg. It's not as fast, so for that application it runs a little bit slower. And then also on top of that, you either have to be, you need some kind of buffer to dither with, and with positional dithering or the Bayer matrix, I just basically say I'm at this pixel, I'm going to look up in this matrix and know what to render. With Floyd-Steinberg, you need a scratch buffer. I need a buffer that's at a higher resolution. So typically, when I originally did the Pebble GL engine, I was using a 4-bit buffer So I could render 16 shades of gray. And then I would then dither from that buffer, like I'd run float sideburn on that, and then copy that to the screen. But that meant that I was wasting 12K of RAM for my application. On top of that, doing a mem copy from one to the other, which was slowing down the applications. With the order dithering, everything's much quicker, and code-wise, it was just that one function that we saw earlier.
Architecture diagrams of what's in the watch. I did a search just to
Sure. So
familiarize myself.
on the Pebble wiki page, we have a really good diagram of it. I actually have it here too. Let me see if this one has it. Okay, so I don't have it on with me on this, unfortunately. Nope. Sorry, I don't have. We have a really good diagram that shows the internals of the microcontroller we use. But it's a Cortex M3. We have 128 kilobytes of RAM. We run at we run at 64 megahertz. We have 4 megabytes of on the chip flash, and that's what we use for like resources and storage. So that's like all the fonts, all the icons, all the bitmaps. And then on top of that, we also have a Bluetooth controller with both classic and LE. So we can do low energy, we can do like iBeacon, that kind of stuff. And on top of that, we also have a vibrator, so you can get vibrations to the Pebble, magnetometer, so we can do a compass, luminous sensor, so we don't turn on the backlight during the day. And I think that's it for components. Yeah.
Is there Wi-Fi connectivity?
No, there isn't. It was one of the hard trade-offs we debated about early on was how connected do we make it? And we basically figured that having it be able to talk directly to your phone means we can leverage the phone for everything that you already signed in on, like all of your accounts, your email. So there's no dual signups that you have to do. Like I don't have to log in on my Pebble to read my email. At the same time, one of the tricks we do with the Pebble, and let me just pop this one back up. So we have like a couple apps in here, like on the far right, we have Yelp, like the Pandora, all those apps. Yeah. So a lot of our more intelligent apps, the way that we write them is that you write embedded C for the UI, for the display that's on the Pebble, but all of the web part of it, all of the communication connectivity, you could write in JavaScript. And the little trick we do is that the Pebble app that's on your mobile phone actually hosts a JavaScript interpreter. So we run the web part of the app on your phone, where we have a full HTML5 implementation with JavaScript and dual core and lots of RAM. So we can do anything we want in JavaScript. And on the Pebble, we just run the display that can get messages. Previously, we had implementation called HTTP Pebble that allowed people to do HTTP requests directly from the Pebble through the phone to the web. So you could do like an RSS reader, or you could do like really simple like pings and like puts and gets from the web. But everyone was asking for more powerful languages like JavaScript. And we had the idea that we already had a mobile app on the phone. If we just built in a JavaScript interpreter, our apps could become instantly more powerful. And we also, at the same time, baked in the App Store into the mobile app. So we had everything in one spot on the phone with all that power. And on the Pebble side, we have all that connectivity. And yeah.
Is there any work in taking that even further and, let's say, compile some bytecode and then load it on the phone and actually, sorry, on the watch and actually run that on the watch?
So we've had a couple people do fun ports like Python to the Pebble, or Rust or JavaScript, and it's always a really good like demo of the concept. But one of the things that you lose there is that you still need to communicate with the world somewhere. We actually have a really neat library called Pebble.js, where it allows web developers who don't want to do embedded C, who don't want to write low-level code, to do everything in JavaScript. And then what we do is we install a native app on the watch that just handles drawing commands. So the JavaScript, you'd basically say, I want a menu, I want it with these texts and these icons, and you do it all in JavaScript. So if that's familiar to you, that's very easy. And then we just have the app on the Pebble understand a protocol between the two and render all of that. And we've had a couple more advanced apps coming out from that, like apps that can like look at Flickr images or read like Hacker News or that kind of stuff.
You know, for the embedded C / JavaScript kind of app, compared to Pebble.js, does Pebble.js still need like the app message in the background?
Yes, it does. It hides it all under the hood, so you don't have to worry that it's there.
Oh, you don't?
So basically, you just create the app from a high-level perspective of what you want to draw and when you want it to be shown. And basically, Pebble.js takes care of all the messaging for you. So you don't worry about copying data from here to there. So yeah, so Pebble.js is really great if you just want to write everything in JavaScript and basically just, you know, like you can make a pretty advanced like email reader or image viewer. And it'll do all the work of putting things on the Pebble for you. Cool. So one of the things I didn't really get to show off today was we do have 2 platforms we develop on. We have both a native toolkit, so if you wanted to write everything on your PC, use Emacs and Vim to compile, you can. At the same time, we have a cloud SDK called Cloud Pebble, where you can write all of your code in the browser. You click a play button, and it installs it to your PC. I can always just bring that up. Maybe. There we go. Okay, so here I'm just going to go to, so this is a precursor to Pebble.js, where it was allowed us to write just all JavaScript, but it wasn't as powerful as Pebble.js. So this is probably 6 or 8 months ago, but it was nice in that I would just write all my code in the browser, and then we can't see it on the screen here because it doesn't scale well, but on the far right there's a play button, and you just click that, and it sends it directly to your Pebble. And it's nice in that our Cloud SDK has auto-completion, it has debugging and logging. Or sorry, when I say debugging, I mean that you can log from the app and see messages and errors. And it also comes baked in with some of the more popular example apps. So you can create in here like an example watch face or an example app message example. And you can start hacking on top of that code without having to copy and paste it from some online example. Cool. So we kind of do the same thing that Apple TV does, where it's local. So this is actually running some code client-side. And basically, I can either go under settings, and I can set my IP. So right here, I can put my phone's IP. And that actually shows up on the Pebble mobile app under developer mode. Or if you're on an iPhone, we actually do auto-discovery, where the 2 apps do a little handshake, and it reports back your IP. That only works on the same network. So we don't have to worry about a security model. The same thing as Apple does, where you just want the 2 devices to talk when you're at home or in the office. You don't really need it to, you don't need to leave a backdoor for someone to remotely get into.
So when this browser has the compiled binary, it comes to my device through my network.
Right.
It didn't go to Cloud Pebble and Cloud Pebble connect to my device.
Right. So it goes client-side code in the browser over your local network to your phone, and then the phone catches that request and installs it on the Pebble. Yeah.
Are there multiple versions of the watch currently in the market, or is there one platform?
So we have what we call the classic Pebbles. That's the original Kickstarter ones, and then we also have the Pebble Steel. And the Pebble Steel is a little more industrial design. It's a Gorilla Glass, so you can't scratch it. It's a little bit sharper image. We have anodized steel on the edges, And then we also have a leather band or a metal band that comes with it.
But in terms of the internals of the platform.
Right. So the only difference between the two platforms is that the Pebble Steel comes with a little charging indicator light. And so when you plug into the charger, you can see like if it's not charged or fully charged. And that's the only hardware difference between the two platforms. It was great for us where the app and the compatibility stayed the same. So a lot of our developers were able to just keep moving forward on their own things without having fragmentation or other issues. But at the same time, a lot of people felt that the original Pebbles weren't professional and enterprise enough. So with Pebble Steel, we actually were trying to move more into a, I don't know, what do you call it, a professional watch space. And if any of you are interested today, at the Pebble booth, we're actually selling Pebbles at a discount, brand new. $80 for the Pebble Classics, and I think $180 for the Pebble Steels. This is quite a deep discount from our original price recently, where it was $250 for the Pebble Steels in Best Buy, and $150 for the Pebble Classics in Best Buy.
Where are most of the Pebble users? Are they still in central US?
Yeah, so we recently had a big developer conference where we had our top 100 app developers come to Mountain View, and we had a really good 4-day session with them where we were hanging out, writing apps, coding, playing with robots. It was pretty awesome. We had a couple people from China, from Germany, from pretty much all over the world. There's a fairly strong contingent here in the Bay Area, and then there's another strong contingent from Canada. And part of that is because a lot of the original Pebble developers, including our CEO, are from Canada. So there's a lot of goodwill and friendship there. And so like whenever we do hackathons in Canada, people are really excited to see us. But we've had some actually rather impressive developers from the middle of nowhere in Kansas, like just the countryside, and they find, for them, they buy the Pebble because it's kind of a neat watch that allows them to be on the farm and get messages while they're working, or driving the trucks or whatever. And then they end up starting to develop on it, and then they write some cool apps. So it's always kind of a neat space for us. Any other questions? Cool. Well, great. Well, thanks for coming.